Let us define instantaneous and total heat flow rate in transient heat conduction. As we know, in transient heat conduction, the temperature as well as the rate of heat transfer both vary with respect to time. So both are variable with respect to time. So let us find out what is the instantaneous rate of heat transfer and total or cumulative rate of heat transfer in case of transient heat conduction. So let us first define instantaneous rate of heat flow. So instantaneous rate of heat flow represented by Q suffix I can be given as rho into V into Cp into dt over d tau, where T is the temperature which is function of time. This T can be found out from lumped parameter analysis. We know temperature at any moment of time is given by T minus T infinity over Ti minus T infinity is equal to exponential of minus h into As over rho V Cp into tau. From this expression, I can get the value of or expression for T as T infinity plus Ti minus T infinity into exponential of minus h into As over rho Vc. Let's say this was the equation number 1 and this is equation number 2. So from putting the value of equation 2 into equation 1, what I will get? The instantaneous heat flow rate Q suffix I will be rho into V Cp T over d tau, and the value of T will be from equation 2 as T infinity plus Ti minus T infinity exponential minus h into As over rho Vcp. Now differentiating with respect to time will give me rho V Cp. Differentiation of T infinity with respect to time will be 0 as it is constant. Ti minus T infinity will also remain constant because both are constant. Then differentiation of e to power minus HAS over rho VCP will become minus H into AS over rho VCP, treating minus HAS over rho VCP as a constant initially, then differentiation of e to power some constant will be E. So it will be exponential of minus HAS over rho VCP. Excuse me. This rho VCP will get cancelled by this. So what I will get, Ti minus T infinity into H into AS. This minus sign will come in the forward, exponential minus H into AS over rho VCP. Here tau is also there, sorry. So this is nothing but instantaneous heat flow rate. We can also write this expression as minus HAS Ti minus T infinity exponential of this entire term can be converted into the non-dimensional form, that is Biot number into Fourier number. So these two expressions are the expressions for instantaneous flow rate in case of transient heat conduction. Similarly, now let us define the total or cumulative heat flow rate in case of transient heat conduction. So it can be represented by Q suffix T. So Q suffix T is nothing but total flow rate from the starting of transient heat conduction to the final time under consideration. So Qi in, and it will be integrate. The Qi will be integrate with respect to change in time from initial to time under consideration. Now we have the expression for Qi, that is minus HAS Ti minus infinity exponential of minus H into AS into tau over rho VCP into d tau. Here HAS over rho VCP into tau is nothing but HLC by K into alpha tau over LC square. HLC by K is nothing but Biot number, and alpha tau over LC square is nothing but Fourier number. This way I can express HAS into tau over rho VCP as Biot number into Fourier number. Now in this expression of total heat transfer rate, HAS Ti minus T infinity are constant, so I can take them out. And I will integrate exponential of minus HAS over rho VCP tau with respect to E tau. So I know integration of ET dt is nothing but, or e to the power mt is nothing but emt power m, where m is any constant. So from this integration formula, I can write this as minus HAS Ti minus T infinity, and this will give me e to power minus HAS rho V dp into tau over minus HAS over rho VCP. So this is nothing but Q suffix T. So let us simplify this. As you can see here, minus HAS will get cancelled by this, and I can take this rho VCP on the numerator, so it will become rho VCP into Ti minus T infinity and sorry for that, here the limit is also there from 0 to tau. So that limit also I have to take into consideration. So if I take tau first, this will become exponential of minus HAS over rho VCP into tau, and if I put tau is equal to 0, this entire term will become 0. So further simplification will give me rho V Cp Ti minus T infinity is entirely multiplied by this. So this will become exponential of minus HAS over rho VCP into tau, and this entire term will become minus 1 because e to power 0 is equal to 1. So finally, I can write this as I can also express this equation in terms of Wyatt number and Fourier number. Ti rho VCP Ti minus T infinity into exponential of minus Wyatt into Fourier number. This entire term can be represented by the product of Wyatt number and Fourier number minus 1. So these two equations will give me the total or cumulative heat flow rate. So this way I can calculate instantaneous heat flow rate and total heat flow rate. This I can also write it as in another fashion for your understanding, rho v Cp Ti minus T infinity e to power minus Wyatt number into Fourier number minus 1. So this way I can calculate instantaneous heat flow rate and total heat flow rate.